Hey everybody, welcome back. Today we're going to do something a little different again. Today we're going to kind of give you guys a behind the scenes look at what we go through in developing a new product. Like kind of the steps in the process and the work that goes into designing something properly. So we're going to start with something that took a little bit of time to get right, but we worked with our driver manufacturer to design for us a new driver. And this is a 2-inch dome mid-range. And they sent this version to us, and it tested and measured really well. I mean, we were really excited about this because it had such a smooth response and such a broad range. It covered a huge range, and it allowed for a really low crossover point. So I got to thinking, I could mount this and mate this with just about anything. I could put one of our tweeters with it and make, any woofer blow it because the low crossover point really opens things up. But I thought, what would really be cool, instead of a tweeter mounted just right up there on it, what if we used a tweeter with a Neo motor on it, and we developed a faceplate that encompassed the two so that it's a pod, and the two are close together so the acoustic centers would get really close. That way, as you move vertically, the time alignment will hardly change because they're so close together, and it would maintain an even response in all directions. So then we got to work on a tweeter to mount with this thing. And then once we had a tweeter that we were happy with, then it was a matter of creating faceplates and stuff that put these things together. And so the process began of 3D printing faceplates that held the tweeter and the mid together in a little pod. And it worked out really well. And then the next phase is, now that we've got that working, and on the test baffles that we're putting it on, we're getting a pretty good response. And we have kind of a finished pod. All right, now what does the baffle need to look like in order for it to have the best response? And I'm going to share a little bit of this with you guys. What we do is we 3D print these baffles, and we mount the pod in here. And as you can see, this little baffle doesn't have a round over on the top, but it has a round over on both sides. And we contrasted that with another one that was basically the same baffle, but it canted the whole thing over so that the surface reflections of the tweeter would be different on each side. So we have a different amount of surface reflection or edge diffraction left and right, so it's asymmetrical. What happens when you do things symmetrical sometimes is, especially when you put a woofer below it that's pretty good size and the baffle width starts getting bigger and bigger, all that surface reflection really disrupts the response. And sometimes the last thing you want is to have a driver right in the middle of the baffle so that it's equal distance from the left and to the right, because then it has the exact same surface reflection causing a peak at the exact same frequency twice. So it makes not just a hump, but an even taller hump. And sometimes we see things come in and the tweeter's centered side to side and to the top. So now we got 3 surface reflections all at the same frequency, and sometimes edge diffraction all at the same frequency, and it really disrupts the response. So when we're working with this stuff and we're starting from scratch, we have the ability to start shifting stuff around on the baffle and seeing where does it create the smoothest response. And I want us to look at some things here to illustrate what happens when you mount something in the middle of a baffle. Now let's look at the frequency response measurements of these raw drivers with no crossover on them. So let's look at the one that's straight up and down, and let's look at the one where it's tilted over. And you notice the mid is basically in the same location. It's just rotated on this baffle here. But the tweeter's closer to the edge on this baffle. So looking at the frequency response of that one, you see that the tweeter's response is different on this model versus this model. It's a little bit smoother. So then we took one of these and we designed a crossover for it that flattened out the response and kind of kept the drivers within their own range. and we created this nice smooth little crossover. And as you can see, it is literally a flat line. I mean, talk about accuracy, extreme accuracy. Crossed at about 2600 hertz or so. It didn't have to cross really low. We didn't have to force the tweeter to cross really low because this mid plays up really high. So it was a range that both drivers are comfortable in, and it was a small baffle, so we're not getting much low frequency reinforcement because it wasn't very wide. But a great response. Now, let's look at a spectral decay. Spectral decay on this thing is phenomenal. That's what we want to see in a spectral decay. We want to see the signal hit it and then it just immediately drop off completely with no ringing, no residual traces, nothing. That is beautiful. Now, the tweeter has a little bit of a peak at the very top. Not so worried about that because that doesn't involve everything we're looking for. Now, let's look at the horizontal off-axis. Now, this is on-axis, and then each line represents moving off-axis 10 degrees. As you can see, it didn't drop off very smoothly there. And I think that was the one where we had the tweeter mounted in the center of the baffle. So it was, sorry for the noise over here, I got a little basket to hold all this stuff. As we move off-axis, we start catching the surface reflections off of the baffle. So imagine you're hearing what's coming straight from the tweeter plus what's coming off the sides. And as you move the sides this way, notice it's going to cause a little bit of a compression off of this side, and you're going to hear a delayed response basically of what's on axis and then what's reflected off of the side coming at you. And at some frequency, it could cause a big peak. And if the wavelengths get up in higher frequency there, they may be a little out of phase and they'll cause it to cancel or be a dipped. So let's look at that off-axis measurement, and you can see that in that range there from about 1,000 to 3,000 hertz, no, 2,000 to about 3,000 or 4,000, there's a humped area there, and it's centered at around 2,600, 2,800 hertz. There's just a hump. It actually increases the output as it moves off axis and causes that big hump. So we realize this isn't going to work. So we then start testing different baffles, and so we go to one like this where we've got a more aggressive radius going off each side, but still had some edge diffraction and stuff off the top. But we're making progress. We're learning some things. How about if the whole baffle were narrowed as it goes up and we put a big round over on it? Let's measure that particular round over and that big of a radius and see what it does. And we start seeing a trend of, hey, this is getting somewhere. We're making some headway here. Then we did one where we rounded the top of it over as well. So we've got smooth radiuses on both sides. And now we're really starting to look, the response is looking really good. And finally, and we've still got the tweeter mid-pod mounted in this one, where we've radiused it back in all directions. And let's look at the frequency response on this, because this is what we shoot for. This is ideal. Let's look at the crossover response first, and you can see we let this tweeter play on down a little lower. It's crossing just above 2K hertz. And beautiful response. Let's just look at it without the crossover. Let's look at just the measured frequency response. And it's not only is it a flat line, but it's dropping down to where we can cross at about 400 hertz. So at that point, we can cross this to anything. And now the important thing. Let's look at the horizontal off-axis. And remember how it looked before in that other baffle. Now look at it in this baffle. Oh, beautiful the way it just drops off in each direction. And then the vertical. Remember I said we're getting the acoustic centers close together. Anytime you have acoustic centers close together, as you move up and down, you're not changing the time arrival very much because they're not very far apart. The vertical off-axis looks fantastic. So of probably any speaker that's ever been in here, I've never seen horizontal and vertical off-axis that consistent. And we haven't even put a woofer with it yet. And the woofer, if we cross it 400 hertz, it's crossing so low, it's not going to change any of that at all on the off-axis. It's going to look beautiful. And, of course, the spectral decay looks fantastic. Now, that's just a little bit of what we go through. That's kind of like cramming it all into a nutshell. This is a year's worth of development and back and forth with the manufacturer on changes to the drivers, getting the tweeter right, changing the faceplate. We went through several different iterations of faceplates to where we got one that actually maintained smooth response on the drivers. We go through tons of stuff and we're developing this stuff. And this particular tweeter mid-pod, we're not going to offer this as a driver. We're not going to sell it in any of our kits. This is developed for one of our customers. It's going to be in some finished commercial models that are going to be fantastic. They're going to be priced really well, and they're going to be a leader in the industry for performance. You will watch. Now, why did I go through all of this? Because we get stuff in all the time that makes me think, why didn't they do any engineering? Why didn't they spend any time in development, researching and trying to create a smooth frequency response if they just put a little effort into the design? Because we get stuff in that just makes me scratch my head. And this is one of them over here. We've got this thing in. This is a new SVS model. It's the new Evolution stand mount, whatever they call it. Ultra Evolution something. Let's take a look at the cabinet first. The cabinet looks cool. Got to give them thumbs up for that. Look at the way this thing's angled. It's like, oh yeah, it's like time aligning the tweeter to the woofer and stuff. Not really, but it is a nice shape, and I like the way they've kind of slanted this in a little bit on the sides here, kind of give this a little curve to where it looks cool. But that's kind of where it stops. The worst thing is the tweeter is spaced too far from the woofer, and it's got almost the exact same spacing to each side and the top. So just like I said a few minutes ago, what that's going to do is it's going to cause the same surface reflection in 3 different directions and the same diffraction. So what's that going to do to the response? Well, it's going to cause cancellation where the reflections are out of phase, and it's going to cause a big hump in the response as all those reflections arrive in phase. Total disaster. The woofer looks good. The nice cast frame. Spider's got a good space between it and the motor structure here, where it's got venting, and it looks good. However, the frequency response on this thing has a lot of breakup at the top of the range, a ton of ringing. So you can't help but wonder, why didn't you just go, instead of this polypropylene cone, just go with a paper cone, do something with the dust cap, do something with the way the surround is attached to get that breakup out of it. And there's a lot of little things you can do to get breakup out of it. I've developed woofers where we've got a prototype in, and it had a little bit of breakup at the end, and I go back to the manufacturer and say, well, what can we do to fix this? And they'll say, well, let me put another sample together. I'll test another one. I'll send you another one. And I'll get another one. It looks exactly the same. Same cone, same everything. No breakup at all. So I said, what did you do to it? What did you do that made it have no breakup? And they said, oh, we just changed the glue that holds the surround to the cone. We used, instead of a glue that dries hard, we used a glue that dries soft. In other words, it dries more pliable, like a silicone-based type adhesive, instead of something that dries hard. And what that did was it softened and dampened the edge where the ringing was, took it completely out. There's a lot of things you can do to get rid of ringing. This thing has a lot. And it shows up in the frequency response. Crossover-wise, exactly what you would expect from a lot of these mass-produced speakers. It is cheesy. And it's got a little iron core inductor on the woofer and an electrolytic capacitor. The tweeter has one sandcast resistor. It does have an air core inductor, and it's got a little Chinese-made capacitor called, and I can't make this up, Zingtot. Yeah, okay. And the connectors, as you would guess, they have steel nuts on them. So they look pretty on this side, but the signal is being smeared with a bunch of steel parts on the inside. And there's no brace inside. The model that they had before this one in the smaller size had at least one brace. Other than that, the cabinet looks good. I mean, it's fairly thick, maybe almost an inch thick. But when it comes to engineering, Well, let's just leave that there. And let's look at the frequency response measurements. So let's see, were there problems with this thing? Let's first look at the on-axis frequency response, and you'll see it stays within a range. It stays within an industry considered standard of plus or minus 2.5 dB real well. But you'll notice at 2K hertz and at 4800 hertz, there's a pretty big peak. And right between it, there's a little bit of a dip right at 3K hertz. So when I see that, the first thing I do is look at the spectral decay. Let's look at that and let's see if there's ringing in those areas. And if we look at it, we can see there is a little bit of ringing in the spectral decay, but it's not bad. It's not real bad, but there's definitely some ringing going on there, especially right there where those two peaks are. You can see it coming out a little further. Then I'll look at the drivers independently because they do this separate binding posts for each for by wiring or by, because this is a selling feature. It's a marketing tool to put two of these on here because they don't cost anything because these are super cheap. And so you loosen this thing off and you knock this little doodad out of it here, and isn't this a great thing for your signal to go through? A little thin piece of tin that's gold coated, and it's gold coated, so it's got to be good. This is extremely thin. I have to be careful with it not to bend it. It looks fragile. So I shoot the drivers independently, and as you can see, there's issues in the woofer's response. Look out there at the end of the woofer's response, and you see there's some breakup there. There's ringing. And if you look at the tweeter's response, you can see that it has those humps in it. Those humps are directly caused by the baffle and the fact that it's centered right in the middle of a baffle. There's an area there where there's a dip, and there's an area there where there's a knee at the end, and it's a very irregular shaped response. Now, the funny thing is, if you look at the horizontal off-axis, where this starts to peak off-axis horizontally is right at 3K. This surface area and this diffraction here causes a peak right at 3K, and that's right where the dip is. So it's kind of one thing countering another. You've got an on-axis response that's got a couple of peaks and a dip, and as you move off-axis, they start to switch places. The peaks start to drop off, and where the dip was becomes the peak. So if you listen to this thing about 20 degrees off-axis, you'll be in a range where those peaks are going to be less effective, where you're not going to hear as much harshness and brightness because those peaks are down. Some of that peaked area is going to reflect past you a little bit. So these things need to be set up almost pushed straight into the room or even tilted out depending on how far away you are in order to get yourself into that range where you're about 20 degrees off axis. Now the vertical off axis, let's look at that. And it's not bad. The vertical off axis does not look bad at all, and part of that reason for that is the crossover point. If we go back to the measurements of the tweeter and the mid pod separately, you can see that it crosses down around 17 or 1800 hertz. At that wavelength, the waves are fairly long, and as you move up or down, you're not changing the time arrival as much. It's not as big of a degree of phase rotation because of the lower crossover point, which means the tweeter's fairly robust. The tweeter will play down low, so that gives me some ideas like, oh, maybe I can fix this. And then let's look at the impedance curve, and we can see it drops to 3.7 ohms, something you definitely have to keep in mind if you're going to be hooking this thing up to hook a bunch of these up to a receiver. It is a low impedance load. Now, next thing I wanted to do was just look at the woofer's curve and look at the spectral decay of the woofer, and then play the tweeter by itself and look at the spectral decay of the tweeter. So let's look at those. Let's look at the spectral decay of the woofer, spectral decay of the tweeter, and where is the ringing coming from? Well, we can see quite easily that the breakup in the ringing at the end of the woofer's response is not being controlled by this crossover, which only has two parts on it. So some of that ringing at the end is going to be clearly audible. It's right there for you to see. That is ringing. And so the tweeter curve looks okay. There's not a lot of aggressive ringing in it at all. It's just an irregular shaped response. So the next thing I did was just look at the raw drivers without the crossover. So just bypass this, hook some wiring up to it, run it out the port, take some measurements. The tweeter's response is rough, and most of that roughness is all this surface reflection and diffraction off of this baffle. if you had this thing on an infinite baffle, or you had it on something like you saw us developing here, where the front baffle rolls back away from it or something, it would probably have a pretty good frequency response. But as it is, and the woofer, you can see how much breakup there is in the woofer's response. You can see it's kicked way up there. Let's look at the tweeter's response, no crossover, and start looking at it in the off axis. And you can see that where that hole is there at 3K, it starts to hump up more in that area. So I'm thinking, all right, this is going to be a challenge. So I just put a crossover together on the back of it and clipped it all together. Took a couple of minutes, 5-10 minutes, made a nice smooth response. Now look at the tweeter's response. You can see it looks good, right? I'm thinking, but I'm also knowing that in the off axis, there's going to be problems. There's definitely going to be problems. So let's look at that measurement, and then let's look at the horizontal off axis of that measurement, and you can see there's no free lunch here. That thing has a huge peak at 3K hertz. I mean, that's bad. I can't use that filter that I created. It has a nice smooth response, but that peak in the off axis is just huge, and it's because they didn't do their homework. They didn't do the development work on this thing to notice that there's a lot of surface area and diffraction there. And what happens when you listen to a speaker that has a lot of surface reflection, it will sound as if it's playing from that baffle forward, because you hear not just what's coming straight out of the driver, but you hear all those reflections off of the baffle. And the wider the baffle is, the more it'll sound like it's playing from that baffle. Now, there are ways you can turn those things off axis, and let's say the drivers just go up one side of the cabinet, and you turn it off axis. You may not hear any of the surface reflection, because the surface reflection then reflects past you. It's all reflecting off to the off axis and not at the listener, because you've towed it out a little bit. But that only works when you have the drivers run up one side of the box. When you have it right in the middle of the box, there's no getting away from it. You can tow it off axis, but you still hear the reflections off of the part that's aimed towards you. So there's no free lunch here. And so to confirm that, what I did was I just took a couple of pieces of no-res, I have some sample strips that I use for testing baffle diffraction, and just stuck it on the sides. Just put a little piece, a couple of inches wide there, or a couple inches tall, not very wide. Stuck it on each side. Let's look at the frequency response and the off-axis response with that little piece of no-res on each side. As you can see, that peak didn't come up near as high as it did, and it starts dropping off a little more evenly, but there's still a lot of surface area there. So I then took and added another piece of no-res across the top. So we're just doing away with basically the edges of the diffraction. And again, the peak at 3K didn't shoot up near as high, and it was more balanced and dropped off. But I can't get away from the fact that it still has the surface reflection. It's still in the middle of the box. You know, some tweeters you can mount that way, and it's not as bad because just of the frequency response of the tweeter, and you can get away with doing that on a lot of speakers. This one does not like it at all. So that's where I am with this thing. I haven't designed an upgrade for it yet. I can definitely design one, and we can get away from these cheesy parts, and we can bring up resolution and clarity and detail and all that kind of stuff. And I can add a little bit more to this filter here and knock that ringing out of the woofer's filter. Out of the woofer's response, I can get a nice smooth response on the woofer. That's not a problem. But the tweeter is a problem. So I may have to compromise. I may have to just pull the levels down and knock down those peaks and leave it dipped. Just create an on-axis dip at 3K so that when you move off axis, it begins to get a little more balanced and has a more balanced room response. Now, with some of our speakers that we've done in the past, and some of the upgrades that we've done on really high-end speakers, a lot of our customers, when they're at this point where they've moved up to one of our kits, or they've wanting us to do a really high-level upgrade, sometimes I'll push that tweeter's response down a little lower in frequency and bring a lot more detail and resolution levels down there and relieve some small woofer of having to play up that high. And there's a lot of improvements that come from doing that, as well as because the acoustic centers are usually fixed. Crossing at a lower crossover point makes it to where as you move up or down, it doesn't change the time arrival that much, and so they don't become as out of phase. So it maintains a more even response up and down, which is sometimes very critical because the ceiling is often untreated and it's the biggest reflection in the entire room. So if you've got a more even ceiling reflection, sometimes that really helps. But sometimes when you do that, when I push that crossover point down, it will tend to pick up surface reflections that it wasn't picking up before because it wasn't playing down that low. And so sometimes I'll let something go with a little bit, not creating a peak, but it may drop off in the other areas and not drop off as much there. So the off axis may look like there's a little bit of a peak there. And in a lot of rooms, or in some rooms that are untreated, that might be a problem. But with our customers, like I was saying, they've moved into really high-end speakers, they're building some of our kits, or they're wanting a really high-level upgrade done to the speakers, they're not putting the speakers in the corners of their room. They're not putting the speakers up against a bare wall and no treatment on the sidewalls. Usually that customer has the speakers out into the room, and they've got some treatment on the sidewalls. So in a well-treated room, some of that off-axis isn't as much of an issue. But in a lot of rooms that are not treated, it can become quite the issue. So I kind of have to keep in mind, what are the customers going to be doing with this? And what's the broad picture? What's the application? And do I need to soften that on-axis or leave a dip there? Because in the off-axis, there's going to be a peak there. And try and find a happy median or kind of a middle ground. That may be what I have to do with this speaker. I just got to revisit it and see what I can do with it. So there's always compromises when stuff comes in and I don't have control over this aspect. When we're developing a product, we can change every aspect, including the drivers. We can work with everything to make a beautiful frequency response that uses minimal number of parts. And then we can put money into high quality parts and get real great results from it. This one, it just perfectly illustrates some of the headache that we have to go through and some of the problems we're faced with when we're trying to fix stuff that comes in and it just wasn't designed or engineered very well. So that's it for this video. I hope you guys enjoyed it. I know it was a little bit of a tech talk, and I know you guys liked that. And you also got to look a little inside to see what's going on. So maybe a little fun there too. It was definitely different, but I appreciate you guys watching, and we'll see you guys in the next video.